We usually think of electric current as, well, pretty simple, right? Like water flowing through a pipe. But what if I told you it's not like that at all? What if it's more like a crazy theme park with all these wild rides connected together in one big loop? So let's really dive into that idea. I know it sounds a little goofy, but trust me, this isn't just a silly question. It's actually a super clever thought experiment that's going to make you rethink everything you thought you knew about how electricity really works. All right, so we're going to follow a single electron on this, let's call it a fantastical circuit that was dreamed up by a physicist named Edward Purcell. And his whole goal here, it was basically to mess with our heads, to challenge our intuition and show us just how weird electric current can actually be. Okay, so this is it. This is the map of our Carnival ride. It's one big continuous loop, and there's one really, really important rule. The number of electrons passing any given point per second, the current, has to be exactly the same everywhere. Keep that in mind because it's the key to this whole thing. So what's on the itinerary for our little electron? Well, it's got 4 totally different stages. First, a ride up a conveyor belt. Then it's going to take a dip in a column of water. After that, a super fast free fall through vacuum. And finally, the grand finale, a slow, tedious crawl through a plain old copper wire. Okay, so remember that rule, the current is constant, the same number of electrons are passing by every single second. So you'd think their speed would be pretty constant too, right? Makes sense. Well, that's where things get really, really interesting. Let's start with the copper wire. This isn't just a slow ride, it's the slowest ride you can possibly imagine. We're talking about a traffic jam on a cosmic scale. Get this, for our electron to move just 1 millimeter, that's about how thick your credit card is, it takes nearly 17 minutes. Unreal. But then, whoosh, it hits the vacuum tube, and it's a whole different ball game. That same electron now covers 2 meters in less than 7 nanoseconds. I mean, think about that. We just went from a practical standstill to nearly the speed of light, all inside the same circuit. It's wild. The contrast here is it's mind-boggling. You can't even really wrap your head around it. The speed in that vacuum section is more than 14 orders of magnitude faster than in the wire. That's not just fast versus slow. That's like comparing a snail to a beam of light, all happening in the same continuous loop. So the big question is, how is that even possible, right? How can you have the same number of electrons crossing a finish line every second when some are barely moving and others are absolutely flying? Well, the answer comes down to what current really truly is. And here's the key takeaway. Current is not about how fast any single electron is moving. It's about the total flow. Think about it like traffic. You can have 10 cars pass a certain spot every minute because they're all crawling along, bumper to bumper. Or you could have 10 cars pass that same spot because they're super spread out, but they're all driving at 100 miles an hour. The total flow, the current, is exactly the same. And that right there is the core physics of our whole theme park ride. To keep that flow constant, it's a trade-off. Where the electrons are jammed together, super, super dense, they have to move slow. And where they're spread way, way out, well, they've got to move incredibly fast. This chart really lays it all out. Let's just look at the 2 extremes we've been talking about. The copper wire, think of it like a completely packed hallway. People are shoulder to shoulder, so you can only shuffle along. That's high density, low speed. The vacuum tube, that's a giant, empty field with just a few people in it. To get the same number of people across the field per minute, they have to sprint. Low density, super high speed. And you can imagine the other rides, the water and the conveyor belt fall somewhere in between. Okay, so this has been a really fun thought experiment, right? But it's not just some quirky physics puzzle. This whole idea actually has some pretty major real-world applications. You know that craziest part of the ride, that super fast vacuum drop? Well, that's not science fiction. It's the exact same principle that powers incredible tools like this, a transmission electron microscope. That's what lets scientists literally see the world at an atomic scale. Susie, understanding this wild relationship between speed and density and current, it lets us build these amazing instruments. We can take just a few electrons, accelerate them to insane speeds, and use them to see the fundamental building blocks of, well, everything. So this whole carnival ride idea, it's a fantastic way to show that an electron's speed and the electric current are two totally different things. And it kind of leaves us with one last really fun question from the original text. Has anyone ever actually had the guts and the money to build this goofy theme park for electrons? It's a great reminder, Sometimes the deepest scientific insights can come from the most playful, out there ideas.